All right, change of scenery here. So we're going to use this alternating series error remainder to look at to estimate some sums of alternating series. So you're going to be asked to do this a lot. What's the minimum number of terms needed to estimate the sum of this alternating series? And you're going to be asked to do it to within a certain tolerance. Like we need to be able to estimate so that the error is less than 1 over 200. Okay? So surely we could add a bajillion terms together and we know it would be really daggone close. But we want the minimum number of terms. Okay? Now, what the alternating series error tells us is that the first unused term is the maximum error. So this series converges, right? Because 1 over n squared gets smaller and goes to 0. So you know that this converges. You just don't know what it converges to. So we're going to have to figure that out. All right, so we're going to write out the terms. Now, I wrote out the first few terms here, 1 minus a fourth plus a ninth minus a 16th, etc., etc., etc. We got all these square numbers on the bottom. Well, check this out. By the time I get out to 14 squared and 15 squared, 1 over 15 squared is smaller than 1 over 200, right? I'm not looking for the first term that is larger than 1 over 200. I think I was thinking about the denominator there. The first term where the denominator is larger than 200 is going to be the spot that I can cut off. Skirt! Hit the brakes. Don't add that term. Add all of the terms right before it. Remember, we want the first unused term to be smaller than 1 over 200. So 1 over 225 is the first unused term. Well, how many terms did it take? From 1 all the way to 4. It took 14 terms. Okay, because the 15th term was the first one that was smaller than 1 over 200. Okay, so that's a nice little application of the alternating series error or alternating series remainder. All right, let's take another look. Now this one's going to be rad. It's going to be really rad. All right. So example 3, we looked at this series. And now we confirmed that it converged, right? Because the terms got really small, really quick, and they also went to 0. But what's the sum? Okay. All right. Check this out. Now, we want to show that the first 4 terms of this series differs from the actual sum by less than 1 over 300. So let's do that. All right. So we're going to write out the first 4 terms and then look at the first unused term, right? Because we want the first unused term to be less than 1 over 300. Okay. So the first 4 terms, right there, 1 minus a half plus an eighth minus 1 over 48. Okay, that's fine. But the very next term would be 1 over 2 to the 4th times 4 factorial, which I worked that out. I had to use a calculator and count my toes, but that's 384. And 1 over 384 is smaller than 1 over 300. Okay? So the exact error between the real sum, the holy grail sum, S, and the sum of the first 4 terms, S sub 4. So to use some of that notation I showed you earlier, the difference, so the exact error, the absolute value of S minus S sub 4, which is this R sub 4, this exact remainder after 4 terms are added, that difference is less than that first unused term, which is 1 over 384. So that's what I've written out right here, kind of using that same notation that you saw with the alternating series remainder. So the error is less than 1 over 300. In fact, it's less than 1 over 384. So that's even more precise than what we were asked for. Now, here is what's going to blow your mind. It's going to be crazy right here. Check this out. Now, I know, because I am a minor math deity, I know that the sum of that alternating series is 1 over the square root of e. It just is. Okay? Duh. Let's see what is going on. So here are some screen captures of using my calculator. So here is the sum of the first 4 terms, which you might remember. Was 1 minus a half plus an eighth minus 1 over 48. Well, that was 0.604, blah, 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 blah. Well, then if I add one more term, remember, jumping back and forth, right? If I add one more term, the 1 over 384, I get 0.60677, blah, blah, blah. So this Grail sum has to live in between 0.6041, blah, and 0.6067, and blah. That's a pretty small window. Well, check it out. Dun, 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 dun. 1 over the square root of e is 0.6065. That is in between those 2 approximations. Well, even further, dig this. Okay? So the actual difference between s, the real sum, and the 4th partial sum, right? So the sum of the first 4 things is this exact remainder. So using the terminology here, I'm plugging in. This is 1 over root e minus, these are the first 4 terms. This is the exact error, right? So I did that in my calculator, and I found out that that was you take this 0.6065 number and subtract this number right here, 0.604, that one, you get 0.023639993. And there's more, but that's all the calculator could handle. That number, 0.002, is less than 1 over 384. The exact error right there, 0.0023, is less than 1 over 384, 0.0026. Oh my, are you kidding? Stuff is awesome. That is rad. Now, I'll let you in on a little secret. You're going to know in a couple weeks' time why that converges to 1 over root e. You're going to know it. And I'm like, it's not just going to be something you remember. You're going to know why. And you're going to just like flip your lid when that happens. Whew! Man, I can't wait to show y'all. So that's alternating series remainder. Now, a little quick word about absolute and conditional convergence. So this is something, again, on the AP exam. Absolute convergence and conditional convergence. Absolute convergence, what that means is if the series, if the all positive version of the series, right, the absolute value of a sub n takes the alternating out of the equation. It just says that if it's the all positive version of the series and that converges, that means the sum of with a sub n is absolutely convergent. So the alternating and the all positive series converge. That's absolute convergence. Conditional convergence says that maybe the alternating series converges, but the all positive version of that series diverges. Okay, that's the difference between the two. And things that are absolutely convergent, if you switch the numbers around and regroup, you always get the same sum, no matter what. Things that are conditionally convergent, you can kind of manipulate them a little bit so you can get like different sums based on how you arrange the numbers. It's kind of weird. But let me give you an example of what I mean by absolute and conditional convergence. So the harmonic series that we looked at earlier. I'm not going to give you too much. It's just these 3 lines here. The harmonic series that we looked at earlier. It diverges, right? 1 over n diverges. But its alternating series converged. Remember that? It was the first example. So the all positive series diverged, but the alternating series converged. That is an example of conditional convergence. Now, compare that to example 4, which was this alternating series with n squared in the denominator, if you remember that. So all positively now, that would just be the p series 1 over n squared. Well, we know that 1 over n squared is a convergent p series. So dig this. For that one, the alternating series and the all positive series both converged. What does that mean? That means that it is absolutely convergent. That's it. That's the difference between them. In fact, all alternating p series converge. But only the ones where p is greater than 1, only those are absolutely convergent. All right, let's see. I got a nice little trick here for you somewhere. Oh yeah, it's right here. If the all positive series converges, if you know that, then the regular alternating one does too. This is a nice little fact, okay? Let me show you how we're going to use this. Remember Hector from the other video? The one that was like cosines on the top, that was like a couple negatives in a row, and then it didn't alternate? All right, dig this. All right, so cosine of n over n squared doesn't alternate. But we can still deal with it, because what happens if we look at its all positive version? If we look at its all positive version, we can say this. Well, cosine is always less than 1, right? I mean, it's only equal to 1 at 0 and pi and 2 pi, every integer pi, will you get a 1. So we can say this. We can say that the absolute value of cosine n over n squared is less than 1 over n squared for all the integers. What does that tell us? That says that since 1 over n squared converges, because it's a p-series, then this less than series also converges by direct comparison. And that means the all positive series of Hector converges. So what do we know about Hector? We know that Hector also converges. What? It didn't alternate, but we still figured it out. That's a nice little tool to have in the old series toolbox. So overall, what do you need to know about alternating series? Well, the alternating series test says do the values have to get smaller and they've got to trend to 0. If they do that, the alternating series converges. Alternating series remainder, which is wicked cool, tells us that we can approximate an alternating series sum to within a certain tolerance. It's just the first unused term is the maximum error. And then the difference between absolute and conditional convergence. So a series where it's the all positive version and the alternating series, if they both converge, that's absolutely convergent. And if only the alternating series converges, that's conditionally convergent. So just some terminology there that you need to know. Next time, we talking about the ratio test. Get ready for